Welcome to my presentation about VirtualFluids CPU module. I am Konstantin Kucha, and I will present you our work today. But before I start, I want to acknowledge for financial support DFG, Deutsche Forschungsgemeinschaft, and TR 277, and for support in computation resources and computation time by National HTP Computing Center. Okay, yeah, what we expected today, or what we'll talk about today, first is theoretical background of VirtualFluids. Then something about VirtualFluids CPU module features. Then about software structure, so-called submodules, and data structure in these submodules. First of all, I start with theoretical background. I am computer science, and it is my point of view for this topic. Yeah, so Martin showed you more detailed information, yeah, this theory, but I want at first very simplify, talk about how it's work. So on the one hand we have Navier-Stokes equation, which describe the flow, the continuum. Yes, it has velocity, pressure, and density, and same is very complex equation. The solution, as analytical solution, is only for a few simple cases for a low Reynolds number, and this is so-called Millennium Prize problem. Yeah, if you solve this, you can get $1 million. And yeah, it's a very complex thing. But on another hand, we have Boltzmann equation, which is more complex equation, which describe flow as a on the particle level, yeah, as a moving of particles, atoms, molecules, because we know everything is consists of these small particles. Yeah, and in principle, we can describe also our world also with particle physics. But it's also very complex equation and relationships here. And what is crazy on this, yeah, we take this more complex equation, apply some discretization for this to solve another complex equation, yeah, and this is a magic. So then we have this elegant formulation for discrete lattice Boltzmann equation for solving Navier-Stokes. Yeah? And from computer scientists from point of view of computer scientists, it's very elegant, or we can very efficient implement this algorithm for computation. Yeah, because we have always some local this collision operator as local operation, and communication only with nearest neighbor. Yeah? And that's all. Yeah? And it's very attractive to implement this algorithm. And we can compute something very efficient. So, because the lattice Boltzmann methods become popular with growing high performance computing, because this algorithm provide good opportunity to parallelization. So, okay, which features we have in VirtualFluids CPU module? At first, it's the same computation kernel, cumulant lattice Boltzmann methods, is in GPU module. Then what we have at the moment in public version of VirtualFluids is single phase flow, implementation for single phase flow, and we can compute laminar and temporal flow. We have grid refinement and MPI OpenMP parallelization and MPI IO restart checkpointing. So on this slide you can see weak scaling for the uniform grid. Yeah. On the link side, this speed up plot, and you can see the performance of VirtualFluids very close to linear scaling performance. We can say for ideal performance scale. Yeah. And on the right side is so-called parallel efficiency. So it shows how efficient is implementation of this algorithm or software in parallel. Yeah? Because it's not always, if you parallelize something, that you have 100% parallelization advantage. Yeah? You cannot achieve 100% speed up with parallelization, because you have always some part of serial code or some part of code which you cannot parallelize really. But in this case, you can see the parallelization parallel efficiency is about more as a 90%, and I think it's good signs that we do our work very well. So, and next slide shows weak scaling for the non-uniform grid. Okay, I forgot. Maybe notice what is weak scaling mean. Maybe not everybody know what it means. It means if we have some system and we increase a number of processes, and we increase also the amount of computation work in proportional to increasing of the number of processes. So, yes?
These are Xeon cores, right?
Sorry?
This is on Xeon cores.
Xeon.
So it says Intel Cascade Lake Platinum, so that's a Xeon core.
Xeon, this is also, yes, I think it's Xeon. Yeah, I'm not sure. Yes, this benchmark was conducted on the cluster, and each node, you can see this 2 Intel Cascade Lake platinum. Yeah, it's earlier it was Xeon. I'm not sure it's the same name as today use Intel also. But yeah, you can Google. It's a CLX AP, also call it. It has two dies, which 48 cores each die, and it's together 96 cores on one node. So yeah, and you can imagine how many processes it was. Yeah, and in this case we have non-uniform grid, and you can see the performance. We have some decrease in performance in this case. Yeah, and the reason why what happens here in this case, we will see later in more details why is we can observe this behavior, but little spoiler, keyword is load balancing, because we have different resolution on the grid, and we need more computation in fine grid and less computation in coarse grid, and so on. It is need special handling. So, okay, here example, some simulation. Yeah. This simulation was conducted in one CRC project about development some new prototype of aircraft, civil aircraft for short distance. And in my sub-project, main topic was noise reduction on the trailing edge by landing of aircraft. And DLR developed this airfoil, so-called DLR F-16, and porous trailing edge. It was consist of porous aluminum. You can imagine as special material. It's aluminum, but it's porous, like a sponge. Yeah. So the porous size was the guys that produce this material could vary this porous size between 120 and 70 micrometer, something like this. So, and it was discovered or investigate which pore size is better, because we need to find compromise between good noise reduction and aerodynamics. If you can imagine, if your wing is porous, it has some holes, then maybe your aircraft cannot fly, because you have leak of lift or something like this. So, and it was conducted some experiments in wind tunnel, and I tried to reproduce these experiments in a simulation. So it was so-called DNS simulation. That's y plus equal 1. If you want to what I say. So it's okay for normal language. It means that we resolve this so-called boundary layer as a full resolution of the aerodynamic on the surface this wing. Okay, and what was also important to resolve pores in porous media, because we want to see what happens then in porous media in this case. So, and it was very challenging simulation. So that we can say, okay, this multi-scale simulation. Yeah, we resolve this boundary layer and porous flow inside porous media. So, and other challenge was Reynolds number 1 million. Yeah, it's very turbulent flow. Yeah, then you have here on the surface turbulent flow, and inside the porous media laminar flow is typical for porous media, because it's so we have this pores, and principle is Darcy flow inside porous media. So, and as here you can see on the picture a very detailed so-called Q-curtain isosurface. Yeah, it shows vortices of this turbulent flow as very turbulent, and yeah, to increase or to speed up this that's turbulent to start, yeah, we use, or it was also an experiment, was used so called stripes, yeah, stripes and special stripes. It's something applied on here on the leading edge to generate, or not generate, to start this turbulent mode, yeah, because you can very long wait before it start to turbulent, yeah. So and that was also some of the point what was investigated, how big should be or how this is the height of the stripes, yeah, or shape of the stripes, how this how this well, which effects this has in the flow, so to speak. So, and okay, yeah, it was a picture, but here is plots which shows, yeah, we was correct with our simulation, very close on the experiment. It's also our simulation not only produce very nice pictures, it's also physical correct, we can say. Yeah, so here on the top is average velocity on the edge, the trailing edge, yeah, and here, yeah, that's different position, and here's Reynolds stress on the trailing edge. So, and yeah, you can see it's result very well, yeah. So, and here video of yeah, the flow above and inside trailing edge. Yeah, you can see how what happens here is this boundary layer, yeah, with lower velocity, and how it flows inside this porous media. And
you're modeling the porous media, or was that in the
it's directly resolved. Everything is resolved. It's direct numerical simulation. Yeah, okay. It's everything
and
resolved.
You said the holes in this porous media. What was the size of those?
Porous size was about 80 micrometer, and the length of the wing, this airfoil, was about 30 centimeter. Yeah, you can imagine. Yeah, this different scales.
So just to simulate something at a Reynolds number 1 million, and you want y plus of 1.
Yeah.
So you have in the order of like 1 the cell height is like 1/100,000 to 1/1,000,000 of the chord length. So if you have like 1,000,000 to 100,000, somewhere between that, cells along the chord.
How many cells along?
How many cells do you have along the chord?
I show you. I show you later. As not along the chord, but yeah, it's summarize my computation cost in principle. Yeah, how many nodes, how many grid points we need totally. It's about 2.7 billion grid points. Yeah, it has of course refinement. Yeah, it was refinement, a very fine grid on the surface and in porous media, and then Corsa, and it was about 6 levels, refinement levels. And I think channel high was about 3 meter. No, something. Yeah, something 2 or 3 meter channel high. Yeah. Yeah. Then we need, of course, very coarse, and in the close to the boundary of channel, and very fine grid on the surface and in the this porous media. So, and yes, I used this. It was conducted on SuperMOOC, so-called SuperMOOC cluster in Munich, and I was I used about 12,000 CPU cores. This was Sandy Bridge, yeah, slower as other CPU. So needed about 1/2 terabyte RAM. So and totally 142,000 core hours per flow over time. Yeah, this one time complete this airfoil. So, and the total core hours was 4.5 million. Yeah, total core hours. And if I summarize it, of course, the 50 days is summarized computation time, but of course this took much more, yeah, because on the cluster it's always full. It's other users, yeah, you need to wait for your in the queue, yeah, if you can compute something and you have wall time, you can compute, for example, only 12 hours, and then you should break up your simulation, and because or system simple break up your simulation after 12 hours. Okay, but for this purpose we have this checkpoint in a restarting system, yeah, which I will show you later. So, and we can compare this result and this computation cost with other. I found some similar simulation, not the same. Yes, this is, I think, NACA 0012 or other airfoil, but in this way, direction, something. Very similar simulation you can see on the build here, on the image. But Reynolds number was lower, not only 400,000. So, and was used this NEC 5000 is I think is spectral code, something based on spectral method. It's also open source, and so was used as Beskov Cray. I think it's cluster in Sweden. I'm not sure, but I think so. Yeah, you see, it's more cores and powerful processor, as in my case, more grid points and more computation time. So then you can see Yeah, which software maybe is more efficient. So
how wide, what is the span of the airfoil you're simulating?
Span was, I think, 10, 10 centimeter, something like this, yeah? 10 centimeters.
1/3 of the core.
Yeah.
Okay.
So,
I think what you're showing is half of it, right? So in the plot we always showed half of it, wasn't it?
which what?
Half of the chord.
The flow system.
I'm not sure.
Here.
Did we show half of
it was complete geometry, but simulated. You see this this stripe, yeah, as you can see.
I was wondering whether we displayed only half of the chord that we simulated, or did we display both? Because the entire, I don't know. Okay, I don't remember.
No, it simulate full length, but a small stripe, yeah, in the middle, but small enough to observe turbulence, or this that we have correct wave number, yeah, or yeah, correct, yeah. So enough to resolve small edges on the surface. Yeah, can see. I can say so. It's correct. Yeah, I think so.
There's a question.
Other question. Okay.
How did you refine around the surface? Was it in the shape of an airfoil tube, or was it a cube?
Yes, as a shape or as a for. I will show in hands-on how we can do it. Yeah, I prepare some airfoil, and we can try also produce the same. Yeah, grid.
There was something on the surface, and then there was some other refinement in the way.
Okay.
Yeah.
Maybe one note, I think the porous part is CT scan, came from a CT scan.
Yes, there's also other aspect. It was also different kind of geometry. For for this part of airfoil was used STL file. Yeah, in principle, the mesh geometry, and this part it was CT scan. This voxel matrix or voxel cloud in principle. Yeah, it needs other art of discretization, other kind of discretization, yeah? And different algorithms and different geometry. Yeah, it's you can see very challenging. Yeah, it's multi-scale, turbulent, and complex geometry, we can say. So.
Were they perform measurements other places and only the trailing edge for comparison, like further upstream on the airfoil? I would say that this is maybe the most one of the most challenging places to compare, I would say, suction side of the trailing edge. It's just, it would be interesting to see how pressure distribution works.
Yeah, pressure distribution. We computed also pressure distribution. And
there was also measurement for the pressure.
Yeah, it was. I don't have now this, but we compare it also. Yeah, with pressure. With pressure distribution on the trailing edge was something. Yeah, something different. I think from measurement, but I think in the measurement they also not measurement really on the porous media. Because it was not technical.
So there were some issues with this pressure, pods, whether they actually are. When you put these pressure probes on a porous media, then you get a random result, whether you are in front of a pore or in front of. So there was, I think. Yeah. This was not really clear.
It was not clear.
But I was more thinking about like the overall, like not the porous part of the airfoil, but the front part.
Yes,
Yes,
also did also pressure coefficient, for whole airfoil compared with the measurement, and the leading edge and the middle it was very nice. On the trailing edge it was some problems, because as Martin said, okay, it's not clear what is the problem. Is problem in the measurement or problem in simulation? It was something not clear in this case.
Then did you actually benchmark the? Did you do some flat plate simulation compared to the spectral code?
Yes, no. We before we start with airfoil, we conducted also simulation with flat plate and flat plate with porous trailing edge, and compared directly to the experiments, and it was very good results. Yeah, and then because this was more challenging, of course. But plate was also challenged, but by plate, okay, you need in principle resolve only top surface, and in this case you need resolve everything.
Yeah, it's just that sometimes these spectral codes have a very high degree of freedom, right? It's a bit different than at least when we compare with final volume, it's always quite hard to compare because they have this different degrees of freedom per cell, you could say, and so on, right? So then, but that also makes them very, accurate, right? Normally for this kind of simulation. So that's why I was just wondering. But
So you can also do some very cool things with these results, with looking into transition and so on. That would be really. That's
okay. I not criticize this other code. It's show you only comparison that LBM solver not slower or not less accurate, maybe.
Yeah, exactly. That's why I was wondering if you maybe have some spectra comparisons under there with some spectral code. But it's just out of interest.
Okay, other questions? No? Okay, then I continue. So, okay, then it was official part, but a little bit to warm up. And now the practical part about it's more close to our workshop. What about VirtualFluids and so which submodules we have in VirtualFluids CPU. So, and here is a list of the submodules, and in principle is mirrored the folder structure in the code. That we can found again these names. If you look in the code folder, in CPU folder, so this LBM data boundary condition, simulation connector, interactor visitor is simulation observer. And now we go in details. As in LBM, I can maybe switch to Visual Studio Code. So, and yes, we have this SLC folder, and here CPU folder, and in CPU okay, sorry, it was here SRC, CPU, and core. Then we have core folder, and here you can see the same names. That's here only sorted alphabetical, and these submodules. And if you open some folder, then you can see in principle, implementation of classes in each submodule. And LBM, at first we have implementation different kernels, LBM kernels, and so, and you can see this, yeah, the names of kernels is K15, K16, K17. So what is mean? So K15 is original cumulant methods, and you can find this kernel implementation of this kernel also in GPU code. K16 is cumulant method for constant density flows. Yeah. So quote unquote incompressible. So and K17, the cumulant method with fourth order convergence for diffusion term. It's this kernel which we use together with GPU, because the CPU code and GPU code use this implementation together. So it's implemented for both version. So and what we have else, okay, this is some abstract classes, and yeah, some classes for definition, for example, some constant and you know, directions and so on, or implementations. So in this D3 code 27 system implementation, some functions. So function for computing, for example, equilibrium or velocity or density, yeah, so on. So, okay, interpolation I will speak about later, yeah, because in first time I speak in first line about so non-uniform uniform grid, and yeah, what we can do with uniform grid and this basic stuff, and in advanced part the more about refinement and how we can yeah, hands-on for refinement. So okay. So then, as Martin explained you, or as Martin also explained about this esoteric split, what we use in CPU code. So, and it is implemented in some, yeah, actually we have so simplified three arrays, so for each split, and each array consists of yeah, for information for each node. Yeah, then we can say, okay, it's more or less array of structures. Yeah, array of structures. So, or other words.
You have to explain what the structures are.
Yeah. Yeah, in this case, it's Fs, or yeah, for each node we have yeah, this populations, yeah, and we store all as in this array is for each node, each element of array, for each node stored populations. So yeah, like on this picture, yeah, that we have, for example, here in split A, node 1, and then populations stored in split 1, then stored in so sequential, and then for node 2, again list of this population or elements of population and so on. Yeah? And then three arrays. So, and in the code we can find this this submodule data, yeah, and here we have some abstract classes distribution array, 3D esoteric twist, and this here is a split. What implement this is a split data structure. So and yeah, you can see we have this principle is implemented so that we have four-dimensional array for split A and split B, which implemented in one-dimensional array. Yeah, and we use index computation to navigate in this one-dimensional array with in principle 4 indices. 3 indices for coordinates and 1 index for population direction. So, and then we have 2 4-dimensional array and 1 3-dimensional array for this split 0. And in this class also implemented different function to access to the data, and so and also in this area we have the function which can get you direct access to this data structure, this pointer, because in the critical infrastructure, we can say in the kernel, where we want to very fast access to the data, without function calling, which typical decrease the performance. We use direct access with pointer. So and this is what we have here: get split A, get split B, get split 0, and this get set methods and set split A and so on. And I can show you. So in the kernel, for example, this one kernel, and so we have this typical function calculate, based in principle for collision, implemented collision operator, and so here, this direct access, before I get the pointer to the split R, for example, and you can see here is implemented direct interrogation with or direct access to this data structure without any function as a special function. So, okay, it's overloaded operator, we can say it's also function, but it works much faster as this classical function, I think. So, and we can see this also in performance measurement. If you use function for the access is much slower as this direct access to the data structure. That what you need to notice, that because in pre-processing or post-processing, where is performance not so critical, typical for comfortable work, we use, and you can use this implemented function to access to the data. Yeah. But if you need maximum performance, you have some critical part, then you need to use this direct access to the data. So, okay. Then we have boundary conditions submodule, and yeah, this table shows some relation between different classes because yeah, the problem was the actual VirtualFluids CPU code based on some previous legacy code. This, Martin explained this long history of VirtualFluids. It was some generation of PhD students which worked on this project, on this code, and just GPU code was started more or less from scratch, and for CPU we want to waste that it was something implemented, it was successful, and we want of course not waste this knowledge and simple throughout, and so and I built my my code also by using these parts, and to combine, but sometimes it was different strategy or different point of use which was implemented, was not compared with my or compatible with my seeing of this architecture, and that I was I needed do some interfaces between these two words. And so we have this BC, so-called BC classes. Then we have BC strategy classes and boundary conditions. So, and in this old legacy implementation, it was so implemented that this boundary conditions was part of so-called boundary nodes, and the implementation of boundary conditions was implemented in one class simple. This was very large class, and everything was implemented with some switch construction and simple switch cases, case, for example, no sleep, this implementation case, velocity, this implementation, it was as a few boundary conditions, and guys was happy with this, but for me that was not enough, because first of all, if you add something, or if you change something, you need always get this class and change in this class. It is huge class, and if you add something, you again change this class and so on. It's not a good software development practice. And because it's big dependencies in your code, and that's always in the change. So. And what's typical you do in this case, well, I think about this, what I can do. If you have typical some amount of algorithms, and you will simple change these algorithms for some purpose, And for this purpose, actually, very good path this so-called strategy design pattern. Yeah, if you know a little bit about software development, there are some so-called design patterns which in principle describes how you can solve some software design problem. So, and I use this strategy pattern, yeah, to extend these boundary conditions classes or made this boundary conditions implementation more flexible in the sense that you can easily add or change, in principle, add new implementation of boundary conditions. Yeah. So, and you can have more different implementation for the same boundary condition, for example, or add new boundary condition which don't exist in this code, for example. Yeah. So, and here in first column is we have okay, this BC is description is also from legacy code. Yeah, it's description for this for boundary condition which is stored in this so-called boundary nodes. This information, if we discretize grid and we decide which nodes are fluid or solid and which nodes are boundaries, for example. Yeah, and we say, okay, this boundaries is pressure, for example, or this boundary is no slip and so on. Yeah, and this part, yeah, this in principle here, which kind of boundary condition? Yeah, we have in principle we have only three or four different boundary condition classes, so we can say. So, and here in the middle is strategies, yeah, for different boundary condition classes and for different boundary conditions, you can say. So we have, for example, we have here pressure boundary condition, or yeah, class pressure boundary condition, yeah, which can implemented with in this case 3 different strategy, yeah, outflow non-reflecting with pressure, and pressure not equilibrium. So on the same names you find again in the code. Yeah, this is the classes of this strategy called the same. And here simple description what it means. Yeah, what is kind of boundary conditions it is in terms of simulation. Yeah, what is if you want to set up your simulation, yeah, first of all you look in the description. Okay, what I need? Okay, I need outflow, for example. I need no slip for walls, and I need velocity. Yeah, and you looked and okay, which BC strategy match my boundary conditions. Yeah, so and okay, so a little bit. I think you cannot see details, but it was also not my purpose. Goes in deep details of this, but only for overview. Yeah, how implemented this, in principle, very complex, but it's from point of view user, and we will see this later in hands-on. It's not so difficult, yeah, because big of part is hidden in these classes. Yeah, you can see it's a very complex thing, and the user should only know which kind of boundary condition and need and which strategy should be set it, yeah, in this case. And then how it is combined or how it is triggered with other parts, yeah, this boundary conditions implementation in the code is totally hide in these classes, okay? This slide is maybe for developer will be interesting to understand this relation, yeah, between these classes. But for user, this only, so overview, okay, yeah, we have this strategy classes, we have this boundary condition classes, this BC classes, yeah, and this what is important to know, of course, this BC array. Yeah, BC array is the array is the same 3D dimensional array which use this one-dimensional implementation, and this array stored actually the yeah, which kind of node at first we have, yeah, this fluid node, solid node, or boundary node, and then which count of boundary conditions are in these boundary nodes. It's good to know, yeah, if you want to extend something, for example, where I can find this information, yeah, as a BC array. You can find this in BC array. So, do you have any questions, maybe, to the boundary conditions? No, okay, go ahead. So then next submodule is simulation. Okay, it's in principle is so cockpit, the or main class where you see is yeah, combined or related to these all classes which I previously said. Yeah, as BC set, boundary conditions and data. Yeah, this is a split, and yeah, it's kernel, LBM kernel, and we have some other classes, yeah, which is simulation observer. I will talk about this later. And we have these grid 3D and blocks 3D classes. And what is it? So we implemented in CPU version so-called block grid. Yeah, it means at first we have some topological grid. Yeah, okay, also it's not consists only of with of blocks. So what mean block? Some, yeah. So here, this you can imagine like yeah, Lego blocks. Yeah, we can put this block together and generate grid. Okay, and block can have other size. For example, yeah, this in case of refinement. About refinement in details, I will talk in second part, but here we talk generally about this data structure. Okay, so and of course each block in the grid or in the same level of the grid has the same size. Yeah, and each block can consist also nodes. Yeah, we store a simple and simple 3D matrix, which stored in this block. So, but topological is the nodes of the grid. Yeah, and then if we look in topological point of view on this data set, we have two levels. This first level is block grid. Yeah, this topological position of the blocks, and then a node grid, which consist of nodes inside these blocks. Okay, and grid generation happens also in this order. Yeah, first we generate blocks and without nodes. Yeah, and we can, it is happens very quickly. We will say, because we have very coarse structure. Yeah, and we don't allocate a lot of memory and so on. Yeah, and then we can decide, okay, if this grid good enough for our, for example, geometry or for our simulation, or we can choose something, yeah, and then later if we see, okay, the block grid is okay, yeah, and then we can add nodes, and again we can decide if it's okay or not, because I know from my experience in working with in this big CRC project with other guys in aeroacoustic and aerodynamic area, they use this commercial software, and the big problems always on our meetings, yeah, which reported the most of time was spent into generation of grid. Yeah, for me it was very surprising because I know only yeah, the VirtualFluids, and for me it was okay. I spent I don't know 20 seconds to generate this coarse block grid and another 20 seconds maybe to generate, and I can see something now. Yeah, I can start simulation, for example, and see first 1,000 time steps, and okay, I can decide is this right or wrong. Yeah, I can show, but the guys over was struggling, yeah, with this grid generation, and always reported, yeah, there's some problem because they also cannot change something in this software. It was some commercial grid generator, commercial software. They can only yeah, call this call center or guys in this firm and then ask, well, yeah, what can I do? I cannot generate a correct grid or correct mesh, maybe. I don't know which methods would use it for this simulation, but it was yeah, very big problem in this case. Yeah. So, and yeah, we have this principle. Yeah, very fast and yeah, easy grid generation, more or less. Yeah, of course, it depends of geometry, and in cases porous drainage, it was also not so easy, but I think it's was much easier is yeah, with this commercial solvers. Okay. Okay, then other aspect which I want to say, yeah, we have these blocks, and in principle, in this some isolated matrix, yeah, on the level of nodes. Yeah, if you see on the level of nodes, so then we can see, okay, because yeah, each block knows only about nodes which are stored in the blocks. Yeah. And not about other blocks in principle, and we need some data structure to communication, we can say, yeah, between blocks. Another purpose of blocks was also better polarization between in distributed memory. Yeah, that's also maybe main purpose. Yeah, because yeah, as you can know, as you know, in distributed memory, we cannot directly access to the yeah, some variables and so on to data from other process. So we need some communication framework, and so on. So, and this data structure was optimized for distributed memory in principle. So, and for communication, we use so-called connector-transmitter concept, yeah, we can say. So here we have some blocks, yeah, and we have different processes. Yeah, so in this case, two processes. Yeah, this process 1, process 2. So inside the process, and other important thing, each block has this inner, normal nodes, normal grid nodes or grid points, and surrounded so-called ghost nodes, yeah, or ghost points. We call this ghost nodes. And we use these ghost nodes, yeah, for different purposes. In principle, as a buffer in most of cases. Yeah, this buffer for some data and for exchange of data and so on. And by grid refinement is used also as a, yeah, if you have refinement on the block age, yeah, block or process age interface, yeah, thank you, process interface. So but inside the process, if like in here in this case, we have uniform grid, yeah, and this is in shared memory, we can say, yeah, this one process shared memory, we can easily access through whole data inside this process, and we not need very complex implementation for this, yeah, communication between two blocks. And in this case, we use so-called direct connector, yeah. So, and if we look in the code, so okay. Yes, this is simulation. Yeah, simulation submodel. I forget to show you. Here, yeah, this block 3D grid 3D class is in simulation class. Is in simulation, and in connectors, and yeah, this classes describes this blocks structure. And here, big submodule with different connectors. So in connectors submodule. So it's also abstract classes and so on. But at the moment, we interested us for direct connector. Yeah, and we have also different implementation for one distribution full direct connector. This, if you have only one distribution, it's typical single phase flow, yeah, standard case. And then we will see later also that we also we are working on multi-phase flow and other things, and non-Newtonian flow. And in other case, we will maybe need more distributions, yeah, and not only one set of distribution, but more. And in this case, we have this implementation for two distributions connector and three distributions connector. So then, and at the moment, this is implemented up to three distributions. You can easily use, if you want to extend the code, and you need mode is a one distribution up to 3 is implemented in code that you this connectors part is already down. Yeah, then you can use this infrastructure directly. So you cannot you don't need to implement something new. So we can say, and we can look in the inside, which is inside this connector. There's a direct connector. This was wrong. Also here. Yeah, you see, it's not so much. Well, this here in CPP is two lines, and so most of implementation is inside of a HPP file, a H file, but this is exchange data. Yeah? So you see this function exchange data. What happens is simple copy between two. It's from regular nodes to ghost layer and other versa. Yeah, that's because we have this ghost layer. Yeah, what happens in shared memory? Because we have full access to this data, then we can simply, if you know this streaming step, we need to stream, and in this case on the boundary of block we stream in this ghost layer, and then by this step exchange data with this full connector infrastructure, full direct connector infrastructure, simple exchange between ghost layer and regular nodes. So, and this is what happens in the shared memory, and we parallelize in shared memory also as well with OpenMP. And earlier I had also implementation of threads with piece threads, so-called piece threads, because early C++ don't support threads directly. It was only implementation in Boost, and in Linux. If you use Linux, of course, no problem, because you you have always these piece threads. And it was some implementation for Windows, but we tried always to develop some multi-platform or platform-independent code. Yeah, that should be runs on different hardware, different operation system. So, and I used this first P threads, then Boost implementation of threads, and then later C++ threads. But I see that on this, if you use these threads, you need take care about this concurrency things, and how you again how you realize the load balancing, and if you take this OpenMP as actually is OpenMP high-level implementation of for threads parallelization, and if you compare this low-level threads implementation with what produce OpenMP, of course you need to tune something, in both cases, because in case of low-level implementation of threads, you should take care about this load balance and so on, and it's also not so easy to implement. In case of OpenMP, this is very simple. I will show you, but you need to take care, or you need to understand what happens. Because it's all simple loss. Use this pragmas and forget. Then maybe you don't have the optimal performance. But if you know what you do, then the performance will be comparable. Yeah, what I want to say, that then we said, okay, we will don't use more this low-level threads implementation, because it's in principle comparable with what produce OpenMP. Yeah, and OpenMP is very easy and understandable. It's, most of C++ compiler support OpenMP, and it also standing in development. Yeah. So, and at the moment we have only OpenMP implementation for thread parallelism in VirtualFluids. Okay, and this thing. Okay, but about about this I will talk in the second part, I think. Yeah, because it's the topic of load balancing and so on. So and okay, and we have, of course, so-called remote, yeah, some remote communication. Yeah, if we in the case we have processes, more processes, for example, MPI processes, and process in distributed memory, yeah, in different computers, or in the same computer but in different processes, where we cannot access directly to the data as a process. Yeah, we need some communication framework. In our case, we use MPI, but that can be other communication framework, because this connector transmitter, which is very nice properties of this concept. Yeah, you can use this not only with MPI. Yeah, you can use this with other communications framework, because it is independent. Yeah, in other projects I implement this also for other communication framework. But it is not in standard this open source version, because it was very specific, yeah, for cluster, and that we developed so some framework for some error tolerance in, yeah, for big simulation, as it means if you run your simulation on the big cluster with more processes, and then happens something, for example, processor is burned on one node. Yeah, it happens. Yeah, yeah, you have more thousand, I know, 100,000 these processors, and very complex cooling system. But yeah, actually this normal, typical case is some server processors, but yeah, this is hardware. This semiconductors, and develop some heat and can burn. Yeah, and okay, you need, and okay, this node then doesn't work more, and you need to, yeah, repair it. But what happens with your simulation? Your simulation is then also done, and you for example, compute something 12 hours before, yeah, and at the end, before you write your results on the hard drive, happens this. And yeah, and you know how expensive is computation time actually, yeah, on these clusters. And because, yeah, after this you need to yeah, reproduce, or start your simulation at the start again. So, and this project was about this, how we can avoid this situation, or in sense that simulation can continue, yeah, and we repair only data on this corrupt node and so on, yeah. But for this purpose, we need other communication framework as the MPI, because MPI don't have this mechanism, yeah. This is a problem. And de facto is the main framework as a parallelization framework for distributed memory. So, and this was, yeah, small outside, but explanation. But okay, in open source and in standard version of VirtualFluids for distribution memory, we use MPI. And actually, this main part, you cannot compile the source code without MPI library. It's yeah, because it's very yeah, this main part of implementation, we can say. So okay, and to communicate between these distributed processes, yeah, we use the code transmitter. So, and yeah, and this transmitter is changeable. Yeah? You can, as I said, we implement transmitter for MPI, and for example, if you have other communication framework, you can develop your own, for example, with TCP, I don't know, and use and implement a transmitter for this communication framework, yeah. Or if you, maybe you have other hardware, yeah, and you need to communicate between these processes, and you can implement specific transmitter for your hardware, something like this. Yeah, this very independent of communication, kind of communication implementation. So, okay, and but we have, as I said, transmitter for MPI. So that implemented the minimum what we have. Okay, and here we have also refinement, and then special connectors for refinement, but I will talk about later in the second part where we will talk about grid refinement. So okay, then we have interactors class. Interactor class we use in preprocess and use it in preprocess and for discretization, yeah, the grid geometry objects and localization and boundary conditions. As in these classes we decided, okay, which nodes are fluid, which are nodes solid, and where is the boundary, and which nodes are boundary conditions, and which boundary conditions should be set on this node. So this important classes for grid generation. So, and we have two kind of interactors. One interactor is D3Q27 interactor used for the called primitives. Yeah, we have some library of classes, so geometrical primitives, yeah, cuboids, cylinder, spheres, lines. So, and yeah, with this geometry you can generate simple. You don't need some STL file or something like this, yeah. And we have this D3Q27 three-phase mesh interactor, which works with STL file. Yeah, that's this special interactor which discretize you give in geometry in form of STL file, form of jungle mesh, and yeah, this three-phase mesh, and this interactor can produce node grid, yeah, for this in this case. So. And here abstract class, yeah, and two important methods you can see here. This init interactor and the update interactor. And init interactor, in principle, starts this discretization process, And update interactor you can use in case if change something due your simulation. Yeah, for example, yeah, you have some maybe moving geometry. It's not implemented. I mean, some fluid structure interaction not implemented. Yeah, this whole process not implemented in the code, but it's some infrastructure is there. Yeah, it's you can change, for example, your discretization in simulation time. So, but maybe it's needed also to change maybe boundary conditions. Yeah, if you want do something with boundary conditions in to simulation time and so on. So, and we have this interactors helper, which is interesting from point of view user, yeah, because if you look in these examples, you can see it will be used this interactors helper. In principle, this only to help user handle with these interactors. Yeah, it's because it's hide some details of implementation, how you apply these interactors to blocks and so on. You need only add. Yeah, you can see three function here. Add interactor. We will see this later in the hands-on, but I can briefly explain. Yeah, here you add interactor to the helper and call the select blocks. That means interactor looks for blocks they are not inside geometry, or which blocks inside geometry, which outside geometry, and it means okay, block inside geometry should be solid, then outside should be fluid. For example, if we something flow over object, we will to simulate flow over object, and some blocks they cross it geometry boundary or geometry interface. This is interface blocks. Okay, then we can on this point now this see, okay, where is how we can generate a grid. So it's the first on course level, this blocks level, and then set BC, then dedicated nodes, fluid or solid on so on boundary and so on. So this three functions. Okay. So, and the next submodule is so-called visitors, and these visitors we are using for most of this implementation of classes using for pre-process, and this implementation is implement the code visitor pattern, design pattern, and it means the purpose, if you don't know what is it, its purpose is pattern is if you have some structure, data structure, and you want to do something with the data structure, but you don't want change this class which describes the data structure, and you want easily to extend this implementation every time. This then is good pattern this visitor, because it's independent of your data structure. You implement these visitors and for different purposes, with different goals, and you can easily extend your code. You write your visitor, and so on, and that's it. Yeah, and we have two kinds of visitors: a grid 3D visitor, a block 3D visitor. A grid 3D visitor means you operate on the level of this block grid, or this whole grid, and the block visitor you operate only inside this block. Yeah, if you want to access to, this your code should be the same for each block. Yeah, then you write this block visitor and will be applied automatically for all blocks in the grid. So, okay. This here details of implementation. Again, it's more for developer. I will not go in details. So, and I think this last classes or last submodule for our first part, the simulation observer. Yeah, it's again implementation of design pattern, as you see. Yeah, as software developer are very focused on good software design, and I use different technology to improve this. And so observer pattern is it was developed. If you have some, you can say some process, and we need to do something, or you have not process, you have some data, and we need to access the data is do something, but so not invasive, this. In this case, we have a simulation class, with in principle this the main loop, our simulation, with the time steps, and in this main loop will be applied this boundary condition, collision operator, exchange data, and so on. It's everything happens in simulation class, and but we want to do something in between, maybe. For example, we want to compute, I don't know, CL, or CD, or something, average velocity, something. So, information which we want to use in post-processing then, or we want to change something, to maybe we want to change viscosity, in your simulation, that's after some time steps, but we want, of course, not always put some function in your main loop, and how we can do it, this we use this observer pattern, so we implement this function notify observers. The sense here you have observable, in our case a simulation, and some simulation observers. Observable do something, and if some changes happens, in our case it means next time step, then simulation notify observers, okay, I have now new data, I have new time step, if you want you can do something, and observers always observe, it's become get this notification and saying, okay, I have yes, data is changed, I can apply my stuff, I can compute something and so on, change something. So you can see this implemented in this classes. Simulation is do something with grid directly, is grid changed, yeah, notify the simulation observer call this update function, and yeah, you can easily extend this again. Yeah, if you need something new implementation or something what we want to do with grid during simulation, or get some information or change something, you easily write the simulation observer, which give you this, yeah, opportunity. So, and I think, yeah, that's it. I think I'm, yeah, good in time. So, okay, your question.
Good question. So I want to understand like the application of this observer. Would it be one of application that if someone wants to like change the forcing like on certain cells, you would use an observer, or that would be like you could hard code that into like
forcing is at the moment is implemented directly in kernel.
Okay.
Yeah, because it's other level. Yeah, this was easily, or I think more correct. Yeah, it was also implementation with observer, but Martin said it's not so really physical.
Okay.
Oh.
When we talk about forces, now since we use forces that the fluid acts on bodies, or forces that are acting on the fluid, what are forces?
So the forces are coming from the information that you get from the flow, and then so it's calculated. So the force doesn't.
Okay. Okay.
The force changes.
Okay. I understand. Yeah. Okay. Sorry. Yeah. Sorry. Yeah, I was wrong. Of course, this is really clear case for observer, yeah? And it is implemented. Yeah, you can find calculation force simulation observer. Yeah, because I saw you talking about yeah, forcing, yeah, forces which apply to gravity, for example, something like this. Yeah. Okay. Sorry. Yeah. So, other questions? Okay. If not, then I think, yeah, we have break now.